We're continuing with 5.5, and now we're going to try to use the fundamental theorem in solving a few problems. Let's notice a few rules. Let's say example A. Let's say we're trying to take the derivative of not the cumulative area function, but of this x to a of f of x dx. How do I do that using this theorem? Matching this side and trying to figure out how to match that with this. And I realized, well, the bounds are switched. So what I do is I switch the bounds, and I remember if I switch the bounds, then I have to have a negative sign in front of it. So I put a negative sign and I switch bounds. And so negative comes out of the derivative. ddx of, now this is the cumulative area function, and the derivative of cumulative area function is just f of x. Now, how about this situation? What do I do with this? Now I compare with that one, and I see that instead of x, I have this basically this expression is a function of x. So in this situation, I write it as, I assume that is y, and I write it as dx of a to y f of t dt, which in this case it's going to be dy of the I'm sorry, let's start over. It's going to be ddx of a sub f of y, and according to the chain rule, what we know is this is going to be equal to dy of a sub f of y times dy dx. So basically it's going to be f of y times derivative of 3x squared, which is y, which is going to be 6x. What is f of y? Instead of y, I'm putting in 3x squared times 6x. So you use chain rule to compute this. Again, let's do this one more time and faster. So if you're taking the derivative, and I'm writing it right here, if you're taking the derivative with respect to x of this, it's going to be f evaluated at 3x squared times the derivative of 3x squared. That's how it works every time, according to what we showed up there. Again, now what if, and again, these type of questions are good test questions. And so now let's see, I'm trying to find the derivative, and instead of a and x, I have h of x and g of x. So I'm trying to do the derivative of most general format of this thing. So in this case, you have to remember that this is going to break down into ddx of integral, let's say, a to g of x f of t dt minus integral a to h of x f of t dt. This is according to the properties that we had. It's just going to be from h to gx is from h to a, from a to g, and then a to g is there, but instead of h to a, we switch and we switch sign together, and so that's how it goes. So these are the properties of the bounds. Again, those are good questions too. And now, in this case, according to a similar situation that we have here, the first part, derivative of the first part, is going to be f at g of x times g prime of x, and the derivative of the second part is going to be f at h of x times h prime of x. And again, and this almost is a formula for us, and we use that every time. So let's review the fundamental theorems of the fundamental theorem of calculus. Let f be a continuous function on a and b, and let capital F be antiderivative of lowercase f. Then a sub f of x is the cumulative area function is integral from a to x of f of t dt. And so part 1 tells you that the basically a sub f of b is going to be f of b minus f of a, and that is integral from the definite integral from a to b of f of x dx is going to be equal to the antiderivative of f evaluated at b minus antiderivative of f evaluated at a. Part 2 tells us that the derivative of the area function is going to be basically the f of x itself. And so the two of them together give us that the luxury of solving a lot of area problems, basically. Now, all these stories that we're telling you, it looks like that we have a lot of inverse operation going on. How does the inverse operation work? So this is how it works. You start with f of x, you integrate, and to get the cumulative area function, and you get another function, which is an integral from a to x of f of t dt. And so this is not, this is basically making sure, because we're discussing inverse relation, we want to go from function to function. We don't want to go from function to value at one point. And so that's the f of x integrate to get the area function. That's the integral from a to x of f of t dt. Then differentiate that, and you go back to f of x. And that's what we actually discussed to be the inverse relationship. Now, if you differentiate f of x, you get f prime of x. If you integrate the derivative, then you end up with f of x minus f of a. And so this process, that process was going this way and then coming back to f of x. In this process, if you differentiate first and integrate, you may end up with an f of a, that is the difference in there. So it depends on the a that is down here. So if you're wondering, that direction, that a doesn't matter, but in this direction, that a actually matters. And so that's what initial value does for you whenever we discuss it. Well, here's the initial value, find that constant. So there's a difference between the two. When you go the other way around, you realize that they can be different in a constant, which depends on our initial value. I click a question 4. Suppose f is a differentiable function. When is it true that integral from 0 to x of f prime of t dt is equal to f of x? So let's pause and think, and then come back. So, fundamental theorem of calculus told us, fundamental theorem of calculus told us that the integral from 0 to x of f prime of t dt is equal to the antiderivative of f prime, which is f of t, evaluated at 0 and x. And so this is going to be f of x minus f of 0. And so in here, over here, if f of 0 is equal to 0, then this integral is going to be equal to f of x. If f of 0 is not 0, it's not going to be equal to f of x. So the answer is B. And see, this is the same process here. Differentiate f, then take the integral, and then you may end up with f of x minus f of 0. A is 0 in here, and then it depends on the value of f of 0 if you the beginning and the end value are going to be the same or not. I calculate question 5. The position of a particle at time t is given by a function s of t, and its velocity at time t is v of t. Which of the following expressions represent the average velocity on the time interval a and b? And then the first one reads 1 over b minus a of integral a to b of v of t dt. And then second one is s of at b minus s at a over b minus a. The third one is v of c for at least one value c between a and b. Okay, let's examine the question now. Let's see, what is in the integral from a to b of v of t dt? That is the value, the antiderivative of v of t, which is going to be s of t, evaluated at b and a. And so it's going to be s of b minus s of a over b minus a. So a 1 and 2 are the same. And both of them are the formula that we know for average velocity on interval a and b. Now, what is c? V of c for at least one value, I'm sorry, what is number 3? V of c for at least one value of c between a and b. Okay, so if you remember the mean value theorem, the average velocity is always, if the function is continuous, which in this case it is, the average value is going to end up to be equal to the derivative, if the function is differentiable, it's going to be equal to f of c for some c between a and b. That's the mean value theorem, statement of mean value theorem. So all 3 of them are correct.